Now I want to do an example of weak acid and weak base. So first example we want to do is this question. Find pH of 0.100 molarity HCN. And then they'll say Ka is 4.9 times 10 to the minus 10. Okay, so that's all they'll give you in the question. Find pH of this acid. Here's the Ka. What do you mean? Oh, your homework, it's here, let's take a look at that. Your homework is actually due on Sunday, March 14th. Okay, so you have like the entire spring break and the entire rest of this week. So just make sure you do it because I don't want you guys to forget. My courses is up, SPC is down. My SPC will be down, you can't register for classes, but my courses will be up the whole time, okay? All right, so here's the question for weak acid. We want to do find pH of 0.1 molarity HCN. This is a weak acid because they gave you the Ka. So to do this question, first thing you want to do is know how to write the equation. So the equation starts with HCN, remember, and then plus water. If this is the acid, and then you have the water as base. Okay, and then what do you get? HCN plus water, you get Cn negative. This will be your conjugate base plus H3O positive. This is my conjugate acid. All right, so hopefully everyone gets this part here. This is just the equation from what we learned from the first part of this chapter. All right, the next thing we want to do is after you write the equation, you have to write the formula for Ka. So Ka formula is this Cn times H3O plus divided by HCN because water is liquid, we don't include that. So let's go ahead and put that in here. Divided by HCN. Now we know the formula is this based on the equation. So you have to come up with this equation here. And then you're going to go set it equals to 4.9 times 10 to the minus 10. Okay, so then we do the same thing like we did before in the previous chapter. You have your equation. So the only difference is you have to write the equation on your own. You come up with the K formula as usual, set it equals to the K that they gave you, and then you set up the ice table. So HCN, Cn negative, H3O plus, ICE. Okay, so initially, what do you have? All you have is 0.1 of your acid, so you put that in, 0.1. The other guys are not mentioned, so they're zeros. Okay, and then we gotta know the change, the direction of the change. So we always go towards the side that's 0. If there's no zeros, you have to calculate the Q, compare the Q to K to see which direction it will go. In this case, it will go up with Cn and H3O plus. It will go down with HCN. And because the ratio is 1 to 1 to 1, it's going to be 1x, going down 1x, going up 1x, and going up by 1x. Okay, so then we put this in here, 0.1 minus x, x, and x. Then we can go ahead and set up your K formula here, and we just plug these x values in here. So I'm going to go ahead and write this down here. So this is Cn and H3O plus, so it's x times x, and then HCN is that one, 0.1 minus x. and that equals to 4.9 times 10 to the minus 10. So before we continue here, you want to decide, am I going to use my shortcut? So in this case here, is my K really small, and is it at least 10,000 times smaller than my initial concentration? Yes, it looks like it. So you should use your shortcut. So if we want to use your shortcut, which X do we have to cross out? So it would be this X here next to the 0.1, because we say the X is so small compared to 0.1 that 0.1 minus X will still equal to 0.1. So then we cross this guy out as well over here. These two X's stay because you're not subtracted or added to a number. So the X stays, okay? So now you get your answer as X squared equals to 4.9 times 10 to the minus 11. To get X, you take a square root on both sides, and you get X as 7.0 times 10 to the minus 6. Now, we always want to check, okay? Sometimes they'll put a statement in the question that says, assume K is really small compared to initial concentrations. If that's the case, then they say, go ahead and use the shortcut. You don't have to check. But since it didn't say that here, and we want you guys to practice, the check step, remember, is to make sure that X compared to the initial number is less than 5%. So you take X, 7.0, 10 to the minus 6, the molarity of that divided by 0.1, times 100 to get the percentage. And you get 7.0 times 10 to the minus 3%. So it's a really, really small percentage. So definitely smaller than 5. So it was okay for us to use the shortcut. Okay to approximate. Okay? So now that we know what X is, all we gotta do is find a pH. So how in the world are we gonna find pH? Well, pH is related to X concentration at equilibrium. Hydronium ion concentration is X here. So remember the formula for pH? pH equals to minus log H. And this value here is this X at equilibrium. Okay, so I'll go ahead and write down. Remember, it's the one at equilibrium because once it mixes, it settles, it goes to equilibrium. You take the concentration of H, you can get your pH. So we know that's 7.0 10 to the minus 6. So all I do is plug this value in here, equals to minus log 7.0 times 10 to the minus 6. Okay, and I get my pH, in this case, to be 5.15, and that's my answer. All right, so for 2.2, let me double check, okay? Maybe so what did you use here? So 4.9, 10 to the minus 5. So minus log of 7.07 times 10 to the minus 6, I still get 5.15. So try to check to make sure you're doing it correctly in your calculator. And remember, this is 11 here because I multiply by 0.1 as well. So we have that. And then when you take a square root, you get this number. And then when you take minus log of that value, the molarity of X here, you do get 5.15, okay? All right, so that's one example here. If they give you the, ask you to find a pH for, and they gave you the K. So I want to show you an example where they ask you to find a pH instead, okay? So here, they ask you to find a K instead, they gave you the pH. So it says here, 0.1 molarity of a weak acid, and they'll call it just HA this time, has a pH of 4.25. Find Ka. So again, the questions are only one-liners, okay? But they told you the pH, they want you to find a K, so this is the opposite of what we just did earlier. Okay, so based on the pH here, we got to find the concentration of H at equilibrium. So pH equals to minus log H. And I know that's 4.25 here. equals to minus log of h. So if I want to find log of just h, I'm going to move the negative over here. And then take 10 on both sides because it's log. That gets rid of this term. So h here is 10 to the power negative 4.25. Okay, so let's see what this answer comes up to be. 10 to the power negative 4.25. I'm going to get about 5.62 times 10 to the minus 5. This is my h at equilibrium. Okay, so if I know that h is equilibrium here, this is going to go in my ice table. All right, so since we need an ice table, I want to go ahead and write the equation and write of k, and then we'll set up the ice table. So I want to do the same, same routine so you get used to it, okay? So we got the pH part settled. Let's write the equation. So HA equation plus water, and then you get A minus and hydronium. Okay, so that's the usual, that's a typical generic equation anyway. So Ka in this case equals to A times hydronium divided by HA. And your job is to find these values and plug it in so you can get K. Good thing is we already know what this guy is at equilibrium. So I'm going to go ahead and set up the ice table. HA, A minus, H3O plus. And then you have your ice table. Now, I know this is my H at equilibrium, so I'm going to go ahead and write it down here. 5.62 times 10 to the minus 5. Okay? What's my initial values? So from the question, it says 0.1 molarity of acid. That's all you have. You would not get the equation. You have to learn how to write the equation on your own. Okay? All right. So this one here is 0.1 and then 0 and 0. And that's why I was teaching, I spent a whole class teaching you guys how to write the equations, because if you don't know how to write the equations, you can't start the question. Okay? So you have to know how to write the equation of the acid or the base that they're referring to each time. So let me finish this, and then I want to go back to that previous question. We had some calculated issues over there, okay? So in this case here, if I know the equilibrium is 5.62 10 to the minus 5 and this started at 0, this means it went up by 5.62 times 10 to the minus 5, which is plus x, remember? If this is plus x, A is also plus the same number, which is also plus x. That means A is the same number. Okay, and then if these two went up, that guy would have gone down by the same exact number. So this is minus 5.62 times 10 to the minus 5. You'll notice you see something like this on your post lab in the PHM buffer lab as well. So take this 0.1 minus 5.62 10 to the minus 5. It's such a small number. When you round it back up, you still get 0.1 again because it's really, really small. Okay, so now that you have that, all you do is you take this and you plug it up here. Okay, so in this case here, is A is this guy, H3O is that one, HA is 0.1. So I'm going to go ahead and write 5.62 times 10 to the minus 5 times that again, or you can just write squared, divided by 0.1, and that will give you your Ka. So I'm just going to go ahead and take this number here that I had and then square it, okay, and then divide it by 0.1. And that's my Ka here, so it's about 3.16 times 10 to the minus 8. Okay? All right, So that's this part here, Ka. So remember, this is very similar to the lab post-lab question. They pretty much give you the pH and they ask you to find the Ka. You can do that in this case. All right, now going back to this, let's see how you got 2.2. So 4.9 10 to the minus 10 times 0.1. 4.9 10 to the minus 10, okay, times 0.1 is 4.9 10 to the minus 11. So I feel like you probably forgot the 11 and you used 10, and that's how you got the different answer, okay? Gotta remember we multiplied these two terms together. I didn't really write it out because it was just a simple times 10 to the minus 1, so I just added the 1 and the 11 here, all right? So just be careful of that because you will see a lot of questions. Sometimes it's 0.1, sometimes it's 0.2. But if it's straight 0.1, it's like, you know, you can literally just write that number. And it's sometimes easy for you to forget it goes from 10 to 11 here. All right. Okay. So let's go back to this part. We just finished this question here. So we got two varieties of acid question. Now I want to do a base question. Okay. So the base question will look like this. So here's one example. Find pH of 0.1 molarity molarity NH3. And it says Kb is 1.76 times 10 to the minus 5. So that's all they'll give you. Okay, so when you see this, you see Kb, and even if you weren't sure this was a base because they gave you a Kb here, this has to be a base in this case. So the more you do, the more practice you have, you get used to being able to identify which one's an acid and which one's base. Plus, this is one of the most popular bases, and we keep talking about as well. Okay, this is the stuff in your Windex. So number one step, write the equation. Okay, so the equation is NH3 plus water. Take your base plus water. What does the base do? Base gains a proton. So that's why you have to be really good at writing your equations. The proton came from here, you have hydroxide left over. It's very important to know how to write your equations. I have students writing sometimes the acid equation for a base and then get everything wrong. So the way to check it is, if you're trying to write a base equation, make sure hydroxide is in the product. If you write an acid equation, like you look up here, you'll see a hydronium ion in your product. Okay, so that's an idea of how you can see acid or base equation. All right, now that we have this here, we can go ahead and write the formula for Kb. Ammonium times hydroxide divided by ammonia. And we know the value of Kb equals to 1.76 times 10 to the minus 5. All right, so remember, first thing, write the equation, and then write Kb, and then set the Kb equal to the number. And then we set up the ice table. So ice table. Now this is like learning a new different language. You have to practice. If you just watch me do it, you understand it without practicing, it will be very difficult to do it when you're trying to do your homework or quiz without any extra practice. So you want to make sure you are writing along with me, doing this with me, and then later today, take some time or tomorrow, redo these problems and see if you remember the steps. Okay, you gotta remember the sequence. Otherwise, it's gonna be really hard because you don't really know where to start sometimes. All right, I'm gonna put 0.1 in here because that's from the question. And then we have 0 and 0 of the ions. So that means it's plus x minus x. Okay, so this is 0.1 minus x, x and x. Let's put it back into the Kb, which is x times x, these two here, divided by ammonia, 0.1 minus x. So again, we have this 0.1 down here, okay? And that equals to 1.76 times 10 to the minus 5. So in this case here, we're going to use a shortcut because this is small. It's about 10,000 times smaller than that. So we're going to go for it and then check our x afterwards. Cross this x off. Leave these two x's alone because they're not next to a number, okay? So now x squared is, remember, 1.76 10 to the minus 5 times 0.1, so you get 1.76 times 10 to the minus 6 here. If you can't do this in your head, you can always put it in your calculator and get that same number, okay? Then we want to take a square root of that value. You should get 1.33 times 10 to the minus 3. And then we want to do a quick check, okay? Check your x, make sure it's less than 5%. So take 1.33 10 to the minus 3 divided by 0.1, because that one's my initial. And then you times 100 to get a percentage. And in this case here, it's going to be 1.33%. So yes, it's less than 5%, so we're still okay to approximate. So now that I knew my x is good, they want me to find pH, right? So the trick here with the base problem is pH is what? Minus log H. Do you see a H in this equation in the ice table? Nope, it's not there. So a lot of students try to do the same thing here and they memorize it. Oh, pH is minus log X because they think X is always H3O plus. That's not true. Because when you write a base equation, you have hydroxide coming out in the table, and your X is not H plus. Your X is actually OH. But lucky for you, you know how to do POH. That's minus log of OH at equilibrium. Do you have that value? Yes, it's our X value here. Okay, so POH is minus log of 1.33 10 to the minus 3. Let's get the POH here. It is 2.88. And then, if you know the POH, we can easily calculate the pH. It's 14 minus 2.88, which will give you 11.12. So if this was a multiple choice question, I guarantee you 2.88 and 11.12 are amongst the answer choices. Oh, obviously, this is the right answer. I mean, this is not the right answer, but this one is. A lot of students will end up circling 2.88 because it's the first number to solve. And if you're just going through the motion without thinking of the value that you're getting for X, you might circle 2.88. So what I want to caution you guys is, number one, to think ahead and say, if this is a base and you're giving me a KB, my pH should be higher than 7. Cross out all those values in your multiple choice that are less than 7, so you don't make that mistake. Eliminate those from your temptation, okay? So this is actually POH, and it will be in your answer choice, but you can't circle POH because you're asking for pH, and you want to pick 11.12. All right, so that's a really, really common mistake. The next common mistake is they don't know how to write the equation. Some of them write it for the acid, and then they start off all wrong. The whole table and all the equations are all wrong. Okay, so it's very important to know equation, set up the KB, set up the ice table, and then once you solve for X, identify correctly which one is X. Is it hydroxide or is it hydronium? And then decide, are you getting POH or are you getting pH? Okay? All right, so the next thing I want to do is show you something called percent ionization. Okay? So percent ionization is actually something really similar to what we've been doing this whole time. I wanted to show you. So if you had a generic acid equation, again, I'll write it real quick. So this is my acid. If I add it with water, what we're going to get is A minus plus H3O plus. Okay? Now, if we were looking for something called percent ionization, okay? Percent ionization is basically how much of this acid turned into ions. Well, so specifically, always we just say how much of it turned to hydronium. I mean, just because hydronium tells you the acidity, but it doesn't really matter because this and this is going to be the same number, remember? So the main idea is to take your H3O at equilibrium, okay? So that's how much it split, either this or this, one of them. So all right, the formula is H3O concentration at equilibrium divided by HA of your initial, because in the beginning it wasn't split up yet, so that's the initial. And then after it splits up, after it reaches equilibrium, that value goes there. So that tells you the percent ionization. If you want to get a percent, that's why we multiply by 100 to get the percentage in here, okay? And that will give you a percent ionization. Yes, so the previous question with the pH and pOH, you got to remember they add up to 14. And also, in the future, we will be learning pKa and pKb also adds up to 14. And that was in our last lecture here. I can show you the slides real quick. I mean, not the slides, but the notes that we had. Right here. Okay? All right, so let's go back over here, percent ionization. Now, if you notice, this actually is the same thing as your check step. Okay, so I'm going to show you another example here. But instead of asking for the pH, they're asking for percent ionization. And you notice the percent ionization is literally the same thing as the check step. Okay, so I'm going to go ahead and write down check step. If you ever forget, it's literally the same as check step. Now, in this case here, the question will say find percent ionization of 2.5 molarity HNO2 solution. And they'll say Ka is 4.6 times 10 to the minus 4. Okay, so that's all they'll give you, and they're asking for percent ionization instead of pH. So the only difference here is this one stops at the check step, basically. It's actually a shorter question. But let's go ahead and do it together again. So we are getting a lot of practice. What's the first that we do? Number one, we write our equation. So let's write our equation out. HNO2, this is an acid. So I have to write an acid equation, okay? Acid loses the proton, so you get NO2 left behind as your conjugate base. And you get hydronium ion as your conjugate acid. Okay, so if you still don't know how to write equation, you have to go watch the video for the class before this, where we were learning, the first class of chapter 17, where we were learning about how to write equations. All right, so now that you have that equation, we'll go ahead and write the K formula, in this case Ka. So Ka, remember, always the equation has hydronium, so Ka will have hydronium in it. So it's NO2 negative times hydronium ion over HNO2, and we drop water because it's liquid. And that equals to my Ka here, which is 4.6 times 10 to the minus 4. Okay, so and then now what you want to do is do the ice table. So the ice table here is HNO2 and then NO2 and then H3O plus ICE. All right. So once we get our ice table in, we want to fill it up. Our initial of the acid is 2.5 as given in the problem. There's no mention of these ions being put in, so that's 0 because they didn't put anything in. So because there's a 0, these guys are plus x. That one's minus x, so 2.5 minus x going to x and x. And then I can set it out on my K formula, which is x times x in here. Okay, those guys here, NO2 is x, H3O is x, HNO2 is 2.5 minus x. Set that equals to 4.6 times 10 to the minus 4. Okay, now, once we have this, so I said, Ks was really small, about 10,000 times smaller than that guy. Well, that's about 10,000 times smaller. It's close to it. Okay, so I'm going to go ahead and take my shortcut and we'll do the check step, which actually is a percent ionization anyway. Okay, so let's go ahead and do that. Cross this x out. Now we'll keep these x's here. So x squared equals to now this time 4.6 and minus 4 times 2.5. So it's not shifting the decimal place anymore because it's not a 0.1 right here, okay? So let's take the answer of these two and multiply it together and take a square root of that to get what x is going to be. So it was like 1.1510 to something. And then when you take a square root, I get 0.034. Okay, now, once we get this, we want to do the check step, which is x, right? 0.034 divided by 2.5 times 100 to get the percentage. I get 1.36%. So we're still good, all right? So this is okay. Now, then they say percent ionization. So I wanted to show you exactly the same thing. So I'm going to write side by side here. Percent ionization is actually, it says up here in the formula, hydronium at equilibrium versus HA at initial, okay? What's that? That's X. Okay, let's write it down. 0.034. Hydronium at equilibrium versus initial acid, 2.5. Same exact thing. See that? So percent ionization is literally the same thing as your check step. Everyone good here so far? All right.
Can you explain the check step again really quick with if we're getting 1.36, why is that still okay?
It has to be less than 5.
Oh, all right.
Okay. So as long as it's less than 5, we can safely assume x is small enough to be insignificant, basically. That's why we cross the x out here. So we always do the check to make sure it's less than 5, but it still happens that this time our check step is actually the same as percent ionization. So if they were to ask you in a question, find percent ionization, they really meant it's the same thing as doing the check step. Okay? All right. So we have acids. I did 2 examples and I showed you, the percent ionization part. It's literally the same as the weak acid part here. The only thing weak acid here is once you get the X, you do the check and then you have to go ahead and find a pH. You have to be careful if you're looking for pH, you got to make sure the X is actually hydronium first before you go straight for it. Because if it was a base question, our X can actually be hydroxide. Focus. Okay, our X can actually be hydroxide. You end up getting POH first before you can get your pH. Okay, now, so that was the typical find pH given Kb, find percent ionization given K, whatever, Ka, Kb. In this case here, this one was a little bit different. It says, here's the pH, find the Ka. So this question here is very similar to what we first did in chapter 16, where you know the change of one, you can back calculate the change of the other guy. So from pH, you will find the H concentration, you plug it in your ice table, calculate, the change of one, you back calculate the change of the other 2, and then you can plug it into the K formula. Okay, so all this stuff here doesn't mean anything if you don't know how to write your equations, which is why we spent so much time focusing on writing acid-base equation to begin with. So hopefully that helped a lot. If you still can't do it, just make sure you keep practicing. We have a whole week for you to practice during spring break as well. So just make sure you are doing your practice, okay? This is like speaking a new language. You have to speak it in order to be able to do it. Now, so we've been doing just one acid and one base, right? What if I mix 2 things together, like mix an acid and another acid together? So here's my new question. So there's a mixture of 2 acids, okay? So of acids, we have 0.150 molarity HF and 0.1 molarity HClO. And they'll say find pH at 25 degrees. So they'll have to give you the K values. So I'm going to go ahead and write the K values for you. So HF has a Ka of 3.5 times 10 to the minus 4. HClO has a Ka of 2.9 times 10 to the minus 8. Now these are the two sources. So to find pH, the idea of finding pH is to find the H3O plus at hydronium ion concentration, hydrogen ion concentration at equilibrium, so you can find the pH, right? So we're after the H here for the pH. So the sources of hydronium ion are from HF, because it splits, and then HClO, because it splits, and another source is actually water, because anytime water you have here, you have Kw, it splits too. Remember, it gives you a little bit of hydronium, but a very, very small amount, because the K is so small for water. So what you end up doing here is there's 3 sources, but these sources are 10,000 times smaller than the first one, and another 10,000, like way, 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 way more than 10,000 times smaller. So they're super, super small, these 2 contributions here. So what you end up doing is when there is a mix of acid, pick the strongest one and work with only the strongest acid in the list. You ignore all the rest of it. The other stuff is just distraction. So if you see a question on your test or quiz where it says, here's a mixture of acid, find the pH. People get so confused. You're like, well, there's 2 acids. How do I do it? Well, all you do is you pick the stronger one and you work with just that. So these 2 here, we're gonna basically scrap out, okay? So contribution, I'll write it out, to hydronium ion concentration at equilibrium. These contributions are insignificant, so small, they're insignificant. Because K is so much smaller in comparison. In comparison to the strongest acid in the list here. And that's why in the beginning when we introduced Ka to you, I showed you how to judge which one is the strongest in the list and which one is the weakest in the list. Okay, so the bigger the Ka, the more they'll ionize, the more hydronium ion you'll get. So the smaller Ks here, the less they'll ionize, the less hydronium ion, they become insignificant. So this becomes literally a problem with just HF. Okay, so by now we've done this a few times, so let's go ahead and try to work on a problem as if it was just HF. So how do you do it? Number 1, write the equation. So there's a lot of practice that we're doing today, but sometimes that's what you need to get familiar and get better at it. HF plus water, I'm writing my equation, F negative, and hydronium. It's a good thing I have hydronium here because I have an acid equation. I expect to see hydronium in my equation. So in this case here, Ka is F negative hydronium ion divided by HF, and that equals to the value that's given. So these K values have to be given, otherwise you have no way of checking it. So on the homework, they don't give you the case right in the question. You'll have to search in the table, the appendix table, the list. They'll give you a link to find the case there, okay? So in this case here, you have these 3 values from the formula, and we'll plug in the Ka value of 3.5 times 10 to the minus 4. Now, what's the next step? We set up our ice table. So ice table is going to get set up. HF, F negative, H3O plus, ICE. Okay, so with the ice table here, we have to put in our initial concentration. So there were 2 acids in the question. So which acid are we looking at? We're going to look at HF. So we'll put 0.15 in our initial. This one is as if it wasn't there because it's so small in comparison to that. The Ka is a lot smaller. Okay, it will give you some H, but it won't be significant enough to change the pH value. So HF is 0.150. These are 0, 0. So that's plus X minus X. So again, you see how it's like pretty much the same stuff over and over. So we do 0.15 minus x, x and x, and we'll set it up here on the Ka equation up here. X is F, another x for hydronium, and then 0.150 minus x is for HF, and that equals to 3.5 times 10 to the minus 4. Because it's 3.5 10 to the minus 4 and 0.1, we're kind of skirting the danger zone because it's like close to 10,000, right? I'm just going to go ahead and do my shortcut and then hope for the best. Hope it's less than 5%, okay? So we'll do x squared equals to 3.5 times 10 to the minus 4 times 0.150. And then take a square root of that product, the answer there. And you end up getting, let's see, let's do it. 0.15. It's 5.25 10 to the minus 5, and I want to square root that value to get 7.2 10 to the minus 3. Okay, so then we do our check step. As long as it's less than 5, we should be good. So 7.2 10 to the minus 3 over 0.15 times 100. 4.8. Oof, that was close, but good enough. All right. So with that, they wanted you to find a pH. So we know our x is good. So this is my x here. That's my, what is x here? X is concentration of hydronium at equilibrium. So minus log of H3O plus at equilibrium, which is x in this case. We'll give you the pH, remember? So it's minus log of 7.2 10 to the minus 3. And you should get a pH of 2.14. Okay, so gotta check. If they ask for a pH for acid, it's straight up just a pH right away from the X. If they ask you for a pH for a base, you have to get the pOH first and then calculate the pH. Okay? All right, great. So those are your answers match. That's perfect. That's good. Thanks for checking it for me. So here's a mixture of acid problem. Now, if you have basically a polyprotic acid, so that means if the acid contribute more than one H at a time. So I have a list of some polyprotic acids as well, if I can find it. But actually I wanted to write it out on our notes as well. I wanted to show you that. So maybe I'll go ahead and write it out. Yeah, here's the list first. So polyprotic acids have multiple H's that come off, okay? So we have, now the weird one here in this list is sulfuric acid. It's super weird because the first acid is actually strong dissociation, and then the second one is weak. But then the others are like K and K. You see how like, because there's 2 protons here, so they have 2 sets of Ks. And then you have 3 here, there's 3 sets of K. So this one here, citric, has 1, 2, 3. So there's 3 sets of K here. And then there's 2. So you just see how many H's they have that can split off from the structure. So they'll give you the K list here. Now, one thing you can notice about is usually the first K is the strongest and the other 2 Ks are weaker, a lot weaker. So focus in here. See how this is 10 to the minus 3, 10 to the minus 8, 10 to the minus 13. So it becomes the same question. If I give you a polyprotic question, you just work with the strongest Ka equation. The other 2 are too small to be significant, so you work with just the first one in this case here. You work with the first one in this acid for citric acid here. So basically, like if you have another acid, ascorbic acid, you work with the first one. Carbonic acid, you work with the first one, because the other one after that are a lot smaller, and the contribution of H plus is not significant anymore. Okay, so the only one that's weird in this list is the sulfuric acid one. So I'll show you an example of sulfuric acid calculation. That one is going to take a little bit more math, so I don't put that on the test or the quiz, but it might show up in your homework and extra credit, so I want to show you guys how to do it as well. But so let's talk about polyprotic acid, how it like basically gives off multiple protons. So I wanted to do with one that has the most protons. In this case is phosphoric acid. Okay, so phosphoric acid is a weak polyprotic acid here. So I'll write out polyprotic acid. Okay, so if you have a polyprotic acid, to find the pH of a polyprotic acid, we use only the biggest Ka, which is Ka1. The only exception is sulfuric acid. So I'll show you the exception. But for example, if we have phosphoric acid, we saw how in the slides there on slide number 80, you see how there's 3 Ks here? So I wanted to show you why there's 3 Ks. Okay, so the first one is number 1, you have your phosphoric acid. So if this was an acid, you add it with water, we wrote the equation out, you can see it drops 1 proton off. So when it drops 1 proton, you get H2PO4. And then you get hydronium. Great. So that's where our first K is. So Ka step 1 equals to this H2PO4, H3O divided by H3PO4. So I'll write it out. So you understand where these different K values are coming from. It's because you're writing the equation step by step. So I'm showing you, we're just basically practicing writing equations at this point. It's good practice. Okay, and that was the first Ka, and the table gave us a value. It was like 7.5 10 to the minus 3. You don't have to memorize this. They will give you these values. You can look it up from a table, or it'll be in the question itself. And then the second, there was another Ka. It was a lot smaller. That Ka was like 10 to the minus 8, and then 10 to the minus 13 for a third one. We'll go ahead and write the equation out and show you. How do you write the second one? Is you take this guy and you continue dropping another proton off. So another acidic equation, and then you split this guy, take a proton off, you get HPO4 2 negative this time. Okay, and then the Ka2 stands for HPO4 2 negative times hydronium divided by H2PO4 negative. That was a smaller number. It was like 6.2 10 to the minus 8. See how much smaller that is? So from step 1 to step 2, yeah, this guy gives hydronium, but look at how small the contribution is. Because the K is so small, there's going to be very, very little of H. It favors this side. And this one's a lot bigger. This H contribution is a lot bigger. So that's why we focus on just the first K. Okay, so if you were to do a polyprotic acid, you just pick the first K and you set up the equation, the Ka, and then an ice table, and you solve for just as if it was there was only 1 K there. Yes. Okay, you only use Ka1 here. So I can show you an example of that too. So I'll write out the third one since we're on a list here, but we'll literally do with just the first one, okay? So HPO4 2 minus, I just wanted to finish the sequence here so you can see sequentially it drops off a proton every time. You get phosphate here. So the question might sound scary, but really it's the same thing as a weak acid. Just pick the strongest one and work with it. If it's a mixture, pick the strongest Ka. If it's a polyprotic acid, pick the first Ka because the Ka1 is going to be the strongest one. So Ka for the third one is a formula phosphate times hydronium, and then H hydrogen phosphate, HbO4 2 minus. And then that's a very small value, 4.2 10 to the minus 13. Okay, so remember, you pick the strongest one and you work with it. So I wanted to give you a question here. If I give you a question with H3PO4, you literally work with the first one. Okay, so I'm going to give you a question now with ascorbic acid. Okay, let's go ahead and write that question out. So it says find pH of 0.1 molarity ascorbic acid. So the formula for ascorbic acid is H2C6H6O6. And Ka1 is 8.0 10 to the minus 5. Ka2 is 1.6 times 10 to the minus 12. You see how much smaller the second one is? So we focus on this guy because this one here is insignificant. The contribution to H plus is too small to make any changes. Okay, so we just go with the first step. So they gave a formula for the ascorbic acid. So it's like H2C6H6O6. No matter what the formula is, if they give you a formula, if you know the formula, if they didn't give you one, just pretend that this part is A or something, okay? But anyway, so they give you the formula and then you put it with water. And basically you take one proton off. So take one of these H off. So now you have H left over, C6H6O6. And then because you took a positive one charge, this one is negative one charge now. And then the other side is hydronium. Okay, so you have to know how to write the equations. And then once you write that, we set the Ka again. Ka1 is HC6H6O6 negative times hydronium divided by H2C6H6O6. And that equals to 8.0 times 10 to the minus 5. Okay, so once you have this here, we can go ahead and set up our ice table. So ascorbic acid is a little long formula, right? But it's okay, we just copy it down anyway. HC6H6O6 negative hydronium. And then you have ICE. Okay, so again, we're practicing here, and this is 0.1, this is 0, that's plus x minus x. So this is like, I don't know, the 6th time we're doing this, so hopefully you're getting really good practice. But they're all different types of questions, but the way to do it is all the same. You just have to know the right equation, the K and ice table, and knowing which one to use. Okay, so in this case here, let's go ahead and solve for x, and then this is small, so I'm going to go ahead and do my shortcut, and then we can check it. So it's x times x over 0.1 minus x here from this value. That equals to 8.0 times 10 to the minus 5. We're going to cross this one off, and then we'll check it later. So x squared is 8.0 times 10 to the minus 6, because I take that and that multiply together, okay? And then take a square root of that value. 2.8 times 10 to the minus 3. Now we go ahead and do a quick check. 2.8, 10 to the minus 3 divided by 0.1 times 100. You get 2.8%, so we're still good. All right, now that we're good, the question was asking us to find pH. So what's pH? pH is minus log of H at equilibrium, which is x in this case, which is minus log of 2.8 times 10 to the minus 3. So you should get about 2.55. So you see how it's the same exact way for weak acid. The only difference is for a polyprotic acid, use the first K, the biggest K you can find. For a mixture of acid, you also use the bigger K one. The smaller ones, you just basically ignore it. Okay, so don't feel like you're scared once you see that, because it's literally the same way to do it. Now, the sulfuric acid one is a little bit tricky. So I'll show you that, but like it's just basically you can't use a shortcut if you use quadratic formula. But the way to do it is pretty similar. Sulfuric acid, it kind of sets the preview up for the next chapter for the buffers ice table actually. And then I'll show you in the buffer chapter, we actually can completely skip the ice table and just use a formula after that. Okay, and that's where you're seeing the formula in your lab anyway. So let's go ahead and take a look at sulfuric acid question. Remember, this one is going to take a little bit more time, so I never put this on your quiz or a test, so you don't have to freak out about it. But you will see it in your homework and your extra credits, so I want you to be able to do it. So this one here, it says find pH of 0.0100 molarity H2SO4. And Ka1 is a strong, there's no value because it's a strong acid. And so, but the second Ka is 1.2 times 10 to the minus 2. You see how like it's still a pretty big number. So that's why we can't use our shortcut because, you know, usually it's like 10 to the minus 4, 10 to the minus 5, then we start using our shortcut. So in this case here, the two equations for sulfuric acid, you'll have to write it out. They don't give it to you. All they give you to you is like this. So I'm going to go ahead and write out the equation for you, okay? So the first equation is H2SO4 plus water. This is a one-way street because it's strong. So it's HSO4 negative plus hydronium. This is a strong dissociation. So if it's strong, so that means if I have 0.0100 molarity of this, I would get 0.0100 molar HSO4 and also for hydronium. That's the first step. And then the second step here, you take this guy and bring it down here to dissociate it one more time. Plus water. This one now we have a reversibility where you get sulfate and hydronium. Okay, so with this guy here, we can write the Ka2. It was this times this over that. So it's sulfate times hydronium divided by hydrogen sulfate, HSO4. And that equals to given value of 1.2 times 10 to the minus 2. So it's a big number. All right, so now we got to set the ice table for this guy here. So HSO4 and then SO4, 2 minus, and then hydronium. ICE. So this is where it's a little bit different because there's a strong and then there's a K. So you have to take into account both steps instead of just the one step every time that we've been doing. So what was my initial HSO4? Well, it was before this step happened, the initial HSO4 was 0.01. Agree? Because that one came down here. So I know HSO4 was 0.01. Is there any sulfate in the beginning? Nope, there's none, so no sulfates here, so that one's 0. Is there any hydronium ion in the beginning? Yes, there is. Because before this step can take place, you already made some hydronium. So this one here is not a 0. It's 0.0100. That's the difference. That's the only thing that's different. It's like, you know how we're so used to 0, 0, but this one's not 0 for a sulfate here. I mean for sulfuric acid. So in this case here, we can continue. So now we still go towards the side that has the 0. So because this guy is still a 0 here, one side, even though this has a number, it's still going to go up this way and go down. So it's still going to go to the right. So sulfate is plus X, hydronium is plus X, HSO4 is minus X. So I can go 0.01 minus X, and then X, and then this is 0.01 minus X. It's getting to be too many zeros. I know I'll make a mistake, so I'm just going to drop the zeros for now, okay? So then we can't really use our shortcut because our number is literally almost the same as the K. So there's no shortcut involved here.
Would the H3O plus be 0.01 plus X instead of minus X?
Oh yeah, it is plus X. Thanks. Yeah, because you just follow. Okay, so now that you have this part here, we're going to plug it up here. So very good catch, because that would have made me go through a series of math and make huge mistakes just because of one sign here. So it's always good to check here. That's a good catch here. We want to put plus X. So Ka2, let's go ahead and plug it in here. So we have X here. I'm going to write on the side here. So X, and then that one is 0.01 plus X, and then the bottom is 0.01 minus X. Okay, so we have that, and that sets equals to 1.2 times 10 to the minus 2. Okay, so now that we have this here, we have to solve it. So I'll take this times that on both sides, and then this can be combined together. So I'm going to go ahead and try to bring that down over here so I have more space to write all my math out. So on one side, I have the whole X and that. So I'll do X times 0.01 plus X on one side, and then the other side I have 0.01 minus X times 1.2 times 10 to the minus 2. So this is just a number right here anyway. It's like 0.012. I guess we could write that down. I'll switch it to 0.012 after this. It'll be easier to see. All right, so I'll write it on top here, 0.012, same thing, okay, that and that's the same thing. So we have to open it up here, so this one is 0.01x plus x squared. Okay, and on the other side here, you take 0.012 times 0.01, so you get 0.00012. And then minus 0.012x. Okay, so the next thing we want to do is combine all the stuff on one side and leave 0 on the other side. So it's x squared. Okay, I'll just write it out. This is, I'll flip it around here. So 0.01x, right? And then I'll put the x over there, so that will be plus 0.012x. And then that one goes there too, 0.00012, that equals to 0. Okay, so, and then I can combine these two terms together, so it's x squared and then 0.022x minus 0.00012 equals to 0. So in this case here, I know what my A is. My A is 1. My B is 0.022. My C is negative 0.00012. Okay, and then we use a quadratic formula here. X can be solved as two options. It's minus B plus minus, and then square root of B squared minus 4AC over 2A. And then we just plug our B or C and A all in here, okay? So you gotta be careful when you do this. That's why I don't like to use this on the test, because there's too many numbers. All right, b squared minus 4ac divided by 2a. Okay, that term in there, this little term here should give you like 0.0310. So double check that you can get that. All right, once you get that part, you have two options for your x, right? So the first x, the option is negative 0.027, and the other one, x is 0.0045. So with this term, you put this and you put this plus 1, this one minus, and then divide by 2, you get these two options. So with that, this one here makes no sense because you can't ever have a molarity that's negative. So we cross that one out. So this will be our x here, okay? X would be this amount of molarity. And then we want to find a pH, right? So pH is minus log of H at equilibrium. So why in the world is the H at equilibrium? It's 0.01 plus X. So we'll put that in here. So I'll write out H at equilibrium is 0.01 plus 0.0045. So let's put that in here. And you get your pH of 1.84. Okay, so that one's for sulfuric acid. It's a little longer than I like, so I don't like to put this on the test at all. Okay, all right, so with this one here, we did a lot of examples, but we have acids and we have bases. I only did one base. Base is exactly the same as acid. The only trick with the base is, remember, your table doesn't have H plus right away. You have to get the POH first and then get the pH. That's the only trick to the base. The base is exactly the same as acid. Write the equation for a base, set it up. Just know that you'll get POH first before you can get pH. Okay, so we did acids and base here. Now we want to switch gears, and instead of just looking plain H something, acid and base, I want to look at just ions to see if it can be a base or acid. So remember how in the beginning we were like saying how carbonate is basic and some ions like bicarbonates are basic. Well, how are those ions basic? So I want to write out some of the reasons why, okay? So anions, actually before we do this, I'm going to go ahead and do a quick poll. So for the rest of you who have to run off, make sure you come back and watch the rest of this class, okay? It's a little longer today, but you'll be able to do that. So which one do I want to do today? We did travel weather. Let's do a spice. Do you like spicy foods? Tell us your favorite. Yes, but only with spice, not the heat. Hot and spicy. No spice or heat, please. So it's still kind of like even. Okay, so there's more of us that like hot and spicy. But some, some people like you get sick from it. I actually can't eat it really spicy. It's the spicier the better. It's probably not good, but I do want to enjoy my food. So even though I can handle a lot of spiciness. I try not to eat something that's too extremely spicy. All right, so did we all vote here? Do we like spicy foods? Yes, no. Yes, with just the spices, but not the heat. Some people like it with the heat. Some people say no spice or heat. All right, so far we still got a few people that haven't voted, but majority of us like hot and spicy food. 52% of the class today. All right. Okay, I'm gonna go ahead and end the polling so we can continue here and share the results. All right. So we just finished all the math stuff for acids and bases, and when I talked about ions here. So anions can be a weak base if it came from a weak acid. Okay, why do we say that? Because if you wrote the equation HA plus H2O, you get A negative, right? This guy is the ion, and then you get H3O plus. Now, in general, the definition of weak acid is it's reversible. So this is my acid, this is my conjugate base. Because it's reversible, this A minus can revert itself back to acid, which actually it does a lot of the time because weak acid favors HA. So the weaker the acid, the stronger the conjugate base, the stronger the ion that comes from it. Now, the stronger the acid, for example, if you had a strong acid, like HCl, you know, like a strong acid HCl, HCl doesn't have a reversibility. HCl does this. One-way street. Chloride here, never goes back. It can't go back. So we're saying here, if this anion came from a weak acid, I'll write weak here, this anion will be a basic property. If it came from a strong acid, this anion, completely neutral. This guy is neutral. That one is a base, because they call it a conjugate base. Okay, so if this was a base, okay, so take this guy, if this was a base, how would you write the equation for that guy? So we'll take this guy and write a basic equation. So you take the ion, you want to write a basic equation, and we call this our base now, and then we write it with water. So this becomes basically a basic equation, but we started with an ion, and then you add the proton, you get HA plus OH. Because this is the conjugate acid, remember? And this is the conjugate base. They're paired with water as an acid. So basically you can see how when it's a weak acid, the ion that comes from it can actually have basic properties. If it's a strong acid, the ion that comes from it is neutral. That's why we say chlorine is neutral, and anything that came from weak stuff can have basic properties. Okay, so I'm going to go ahead and write it down. The stronger the acid, the weaker the conjugate base. Therefore, anions from a strong acid are neutral. It's really anions from strong acids, so let's cross it out here. All right, so you gotta remember, this is why chlorine here is neutral. And something weak will have anions from a weak acid can actually be a basic property. So let's try to see some examples, okay? some examples. I'm going to keep writing another one. The weaker the acid, the more basic the anion will be. Now, if you have this anion, nitrate came from what? Came from strong acid HNO3. So is nitrate basic or is it neutral? In this case, because it came from a strong acid, nitrate is neutral, just like chloride was. Okay? And then, what if we did this, nitrite? That one came from a weak acid, HNO2, with the Ka given as 4.6 times 10 to the minus 4. So if that one came from weak acid, this guy here is not going to be neutral. It will have some basic property. Okay? Now, let's look at another ion here. We want to talk about acetate ions, C2H3O2, a negative. It came from a weak acid, HC2H3O2, acetic acid. Ka is 1.8 times 10 to the minus 5. So in that case, because it came from a weak acid, this guy is basic. When you say the ion is basic, you can write a basic equation for that ion. And then you can do whatever calculations you need. You can calculate the pH that results from the basic ion here. Okay, so that's the goal here, to be able to identify ions that can be basic. So anions are basic if they come from a weak acid. Now, let's take a look at cations, okay? So these are anions for now. Let's take a look at cations. So it says here, polyatomic cations can be acidic if it came from a weak base. NH3 is my weak base, right? That's an example. So if I say this was a weak base, and we always write the equation, you plus water, you add a proton, you get ammonium, and you get OH. This guy here is the conjugate acid, agreed? And this one here will be acidic. Why? Because it came from a weak base. Same idea there, because it can go back the other way. So if you were to write this one as an acid, ammonium ion as an acid, you would say, okay, I got this. And then if I wanted to write this one as an acid, you have to add it with water. So you shed a proton off, you get NH3, and then you get hydronium. Okay, and this is called the acid. This was the weak acid. This must be the conjugate base here. So you see how they're related here? So you take this and you can write an acid equation, and because it is true, it said this one does go back this way. So what's cool about this here is when you start writing like the backwards and forwards equations, you notice every time I write an equation for a base, I can have a Kb of this base that's given. If I wanted to write this as an acid, I better have a Ka for this acid. So you see how these two are related here somehow? So the relationship between Ka of this guy and Kb of that, Ka of ammonium and Kb of ammonia is given as this, Kb times Ka equals to Kw. So Kb of ammonia times with the Ka of ammonium will give you Kw, and we're talking room temperature here, which would be 1.0 times to the minus 14. Okay, so you start seeing there's a relationship between Ka and Kb. So we can actually go back to our examples on the last page here. If I were to say this was a weak acid, I'd have a Ka for this guy, remember? And then if I say, well, this is a base, well, I better get a Kb for this guy, okay? And I can say the relationship between these two, well, let me write it in a different color. Ka of the weak acid of Ha times Kb of A minus equals to Kw of 1.0 times 10 to the minus 14. So they're related, okay? So if I wanted to find Kb for these guys, how would we do it? So we can do it, right? We can say Kb of NO2 negative will multiply with Ka of HNO2, and that equals to Kw. We can solve for it if you plug this value in. So 1.0 times 10 to the minus 14 equals to Kb times 4.6 times 10 to the minus 4. See that? So we can get Kb here. So let's go ahead and do that. So in this case, Kb was 2.17 times, or literally just 2.2, 10 to the minus 11. So you can see how you can get the values. If they give you the Ka, you can find the Kb for the anion. And you can do the same for this guy, okay? Let's try that one while we're at it. So if I know Ka is at, what's my Kb for this guy? So Kb for C2H3O2 is literally Kw over Ka of HC2H3O2, which is 1.0 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Okay? So it's like 5.6 times 10 to the minus 10. That's the Kb of that ion. Okay, so it's kind of cool, they're related. So basically, the deal is they never give you the Ks for your ions. They only give you the Ks for the molecules, and you can back calculate with the relationship Ka times Kb is Kw to get your Kb or Ka of your anion that you need. In this case, you know, anions can be will be basic, so you get Kb. And if you had something that was acidic, well, you can get the Ka by still finding the Kb from the given. So the Kb for ammonia, funny enough, is actually also 1.8 times 10 to the minus 5, I believe. I've done it so many times I actually accidentally remembered it. Pretty sure that's it. So you can find the Ka in this case. And so just wanted to show you guys that. And that skill is actually really useful in the problems that we have for ions. Okay, so I'm going to go ahead and write it out. So it says the stronger the base, the weaker the conjugate acid. Okay, if it came from a strong base, the cation is neutral. The weaker the base, the more acidic the cation is. So it's exactly the same as the story for the anion and weak acid basic properties then. Okay, so to contrast it, earlier we were doing HCl, right? If you have NaOH, Oh, I forgot my A. NaOH. Let me just rewrite it. That was messy. NaOH. You know how that splits to Na plus and OH minus? That's a one-way street. It doesn't go backwards. So this guy here, neutral. That's why I always say the sodium carbonate, sodium bicarbonate, the sodium is completely neutral because it came from a strong base. Okay? Now, sometimes there's other conditions that can give you some acidic. So metal cations can also sometimes can be acidic. So earlier we were talking about polyatomic cations, right? Now we're into metal cations. In this case, we clearly saw that one was neutral. If it came from a strong base, it's neutral. But sometimes it can be acidic when it is highly charged and a small size. So for example, like aluminum 3+, Fe 3+, those are like, high charge. And cations are in general small. But you don't want like super big when something on a low parts of the periodic table. That's not small anymore. The higher they are on a periodic table, the smaller they are. Okay? So that's that. Metals cation can be acidic. So in this case here, let's go through a list of a few examples and we'll decide if it's acidic or basic. I mean, if it's an acidic ion or is it neutral, okay? So here's one. I have this ion here, C5H5, NH positive, okay? This is my ion. It came from C5H5N with a Kb of 1.7 times 10 to the minus 9. So that means this guy was a what? A weak base. If that was a weak base, that means this ion here is acidic. And we can calculate the Ka for it. Ka for this guy would be Kw divided by the Kb given. Right? So it would be Ka for this acid is 1.0 10 to the minus 14 divided by Kb of 1.7 times 10 to the minus 9. So let's solve for that. I got 5.9 10 to the minus 6, which is the Ka for that ion. Okay, so it's the same stuff. We can practice it. Now, what about calcium 2+? Came from calcium hydroxide, which is a strong base because it's group 1, group 2 plus hydroxide, remember? So that one here, because it came from a strong base, this guy is neutral. Okay, and then what if we have chromium 3+? Chromium is a small cation and it's highly charged, so it's acidic. And it's pretty small on the periodic table. It's like high up there. So that one's acidic. Okay, so now that we know ions can be acidic or basic, hold on 1 second here. Okay, so let's go ahead and talk about salt solutions, okay? Oh yeah, I forgot it was already 11. Maybe we just finish the salts and we'll do the other parts next time. But I did want you guys to finish, but let's try to see. All right, let's at least do this part here so you can at least do the homework. Classifying salt solutions as acidic, basic, or neutral. So salt solutions here are going to be ionic compounds. So you have a cation and an anion mixed together, okay? So we have a few scenarios. Here's the first one. If the cation came from a strong base and the anion came from a strong acid. Okay, so coming from strong base, this would be neutral, remember? Coming from a strong acid, well, that one's neutral too. Well, that means if you have a cation and anion, they came from strong stuff, this compound, the salt combination here, the solution of it is going to be neutral. So we have some examples. We have Na and we have Cl, right? So that's neutral, agree? And then we have CaBr2, neutral, because HBr is also a strong acid. And then KNO3, neutral. So these guys are neutral. All of them are neutral because each side is neutral. So both of them are neutral. So overall, the compound is neutral. So compound is neutral because both sides are neutral. That one's easy. Okay. What if now you have a combination? So now cation came from a strong acid. This one's neutral still. That's okay. That's good. What if the anion this time didn't come from a strong acid now? It came from a weak acid. So this one here will be basic. So if you have something neutral and something basic combining together, okay, what you'll end up having is overall a basic compound. So in this case here, we have NaC2H3O2, like acetate ion earlier we saw. Now we have CaF2, and then we have KNO2. These are neutral, that side, because they came from strong, this is not acid, this is base. All right, a strong base. NaOH is a strong base, calcium hydroxide is a strong base, potassium hydroxide is a strong base. So those guys are neutral. So I'm gonna go ahead and write down neutral ion, neutral ion, neutral ion. But that guy is basic. This one came from acetic acid, so it's basic. This one is basic, came from HF, which we did a math for pH. This one is HNO2, it's a weak acid. So to know this, they'll give you the K value so you can see, okay? They won't give you the K of NO2, they'll give you the K of HNO2. So this one's basic. Now, when you have a neutral and a basic ion combined together, overall the solution will be basic. Okay, so if neutral, it will be neutral solution. If you have neutral and basic, the solution will be basic. Okay, so let's do the other scenario where you have the opposite. So cation came from a weak base, and then the anion came from a strong acid. Okay, so if it came from something weak, this will have acidic properties. If it came from a strong acid, this is neutral. So like chloride, HCl from a strong acid, that's neutral. Nitrate, that's neutral because it came from a strong acid. Okay, so my example here, maybe we can do NH4Cl. Okay, so this one here is a neutral ion. but ammonium came from ammonia, which is a weak base, so it has slightly acidic properties. So because of that, the solution of ammonium chloride will be actually measuring an acidic pH. Okay? And then we have cations, highly charged, anion from a strong acid. So in this combination, this one here will be acidic. From a strong acid, it would be neutral. So in this case, an example will be aluminum 3+, and you end up with nitrate, because nitrate is from nitric acid. This is neutral. This one, aluminum 3+, is acidic. So this solution here, if you measure the pH, it will actually give you acidic pH. Okay, now, then there's another, a little bit more complicated one. What if both of them came from weak stuff? So like, for example, cation came from a weak base. Anion came from a weak acid. So in that case, you're like, well, who's going to take over? Well, this one's going to be acidic, right? And this one's going to be basic. So what you have to do is calculate the Ka of the cation, compare it to the Kb of the anion. And then you have to decide the stronger one wins, basically. So in this case, if we have NH4F, right? This one came from a weak acid, so it's slightly basic. This one came from a weak base, it's slightly acidic. So you have to calculate the Ka of NH4 and then compare it to the Kb of F negative. Once you calculate it, we actually will be doing that in the next page. You see that the one that's bigger, so in this case, ammonium was bigger, so it will be acidic. Okay, so why are we going over this acidic basic? Because sometimes they'll ask you to calculate pH of these salt solutions. So I wanted you guys to be able to tell that. So we'll do this math on the next page because I have to pull up the K values for these guys separately. I'll write it out because we're going to run out of space here. Okay, so let's go to the next page. We'll just determine if it's acidic, basic, or neutral. Determine if salt is acidic, basic, or neutral. Okay, the first one is SrCl2. Second one is AlBr3. Third one is NH4Br. D is NaC2H3O2. E is NH4F, which we will do the math for. So let's take a look. Strontium and chloride. Group 2, paired with hydroxide, is always neutral. Chloride came from hydrochloric acid, is neutral. So because those two are neutral, this salt solution is gonna give you a neutral pH. Like example earlier, we had like NaCl, that would be a neutral pH. Okay, now this one here, Br came from a strong acid, so this one's neutral. But the aluminum, because it's highly charged, it can be acidic. So overall, this solution is acidic. And then again, Br is neutral. But then ammonium came from ammonia, which is a weak base, so this is slightly acidic. So this solution will be acidic. Okay, and then we have this guy here that came from acetic acid. So don't panic too much because there'll always be hints. I'll show you in a question. If they give you, find a pH solution of NaC2H3O2, they'll give you the Ka of HC2H3O2. So you'll see that because there's a Ka for the acid that came from this one is going to be coming from a weak acid. So this must be slightly basic. And then the sodium here is neutral because it came from sodium hydroxide, which is a strong base. So overall, this solution is basic. Now, for this guy here, we talked about how there's two opposing forces here. This one's acidic, and this one's basic. So we have to calculate, right? So I'll give you the values this time. Now we can actually put them into numbers to check. So from the table, okay, what will be provided on your usual tables and the question itself, they'll give you Kb of ammonia, 1.76 times 10 to the minus 5, and they'll give you Ka of HF. So these values you will be able to find. They're not going to give you the Kb for F minus and Ka for NH4 plus. They will never give it to you. You have to calculate yourself. Okay, so you can look these up from the tables, and on the test question, they will give you these values in the test questions. But the anions and the cations, you have to calculate on your own. Okay. So how do we do that? We use Kw. Remember, Ka times Kb equals to Kw. So let's solve for the ammonium first, okay? So Ka for ammonium is Kb 1.76 times 10 to the minus 5 equals to 1.0 times 10 to the minus 14. So Ka here, you will get about 5.7 times 10 to the minus 10. Okay, this is Ka for ammonium. And then let's do for the next one, we want to find Kb or F. So we use the HF value. Ka was 3.5 times 10 to the minus 4 times Kb. And then that equals to 1.0 times 10 to the minus 14. Okay, so with this here, you have Kb and then you have this. So Kb for F negative will be calculated as this divided by that, and you can get the answer of 2.9 times 10 to the minus 11. And that's how you can say this number is bigger than that. That's why, because Ka of NH4 plus is bigger than Kb of F negative. Solution is acidic. Okay, so with that, I wanted to show you one of the ice table problems that had something like for a salt. Okay, so the first thing with the salt is you have to go through the list like this and say whatever salt they gave you. If they gave you this, if they gave you this. So if they gave you this one, you would have to decide, what am I going to calculate? This is neutral, so I don't have to do the math for that. But this is acidic, so I have to write an acidic equation, set up my ice table, and then try to get the pH from this acidic guy. And then if I wanted to do this guy here, this is basic, so I have to write this guy as a base and set up my ice table and equations like accordingly. Okay, so I'll do the base one because the base one always has the tricky part about to get the pH, you have to get the pOH first. If you have something acidic, you go straight to the pH, so it's a lot, it's not as tricky, but it's really just one extra step. Okay, so let's try one that would be a basic one. So the question you would see looks something like this. It will say determine pH of 0.22 molarity NaF solution at 25 degrees Celsius. And then they'll be nice. A lot of times they'll give you a hint like this. And the NaF salt completely dissociates. To Na plus and F negative. Okay? And then they'll say So they'll tell you it splits to these ions. So then you can, okay, is this neutral? Is this acidic? Is basic? Is this neutral, acidic, basic? You have to figure it out. And it says Ka for HF is 3.5 10 to the minus 5. And that's the big hint. They give you a hint here. They say K of this guy. So once you get this, you can say, well, F here must be basic. This one, they didn't give me the K for sodium hydroxide because it doesn't exist. It's a strong base. And then if they say, assume K is small compared to initial concentrations, that means do the shortcut, no need to check. Okay, so they given a few hints here. So from here, I know that NaF, this is basic, this is neutral. So I'm focusing on finding F here as a base. Okay, and I need to find Kb of F negative. Okay, so let's write the equation out first. A base plus water gives me HF plus OH negative. Again, every time you're writing a base equation, you get hydroxide. Always remember that, okay? So Kb of F negative would be this formula, HF times OH over F negative. So can you use that Ka to say this is the Kb? No, you can't say that. So you have to calculate the Kb. Remember what the Kb was? Kb for F negative is going to be 1.0 times 10 to the minus 14 divided by the Ka that's given, which is 3.5 times 10 to the minus 5. Okay, so I got my Kb here, and I'll put that here. Let's get the answer first. It's 2.86 times 10 to the minus 10, so around 2.9. I'll just write 2.86. Then you continue on. So the first problem is, a lot of times once they see this, they're like, I don't know how to do this, period. You have to determine if this is an acidic, basic, or neutral solution. Well, neutral is just 7, you have to calculate. But since this is a basic, you have to write a basic equation, find the Kb, do not use the Ka given. The biggest mistake is they write the K they write an acidic equation and use the K for this. So sometimes they write the basic equation and then use the Ka without calculating Kb. So that's like common mistakes. Try to prevent that, okay? So once we have this here, we'll go ahead and set up the ice table. So we have our ice table will be F negative, HF, and then OH. ICE. You have initial concentration is 0.22 Na, 0.22 F. So 0.22, and this is 0 and 0, plus, minus 1x each time. And they say, very nice of them, they say use the shortcut, no need to check. So, okay, yay, I can do that. So then I want to set this up, set it to 2.86 10 to the minus 10, which is x times x over 0.22 minus x equals to 2.86 times 10 to the minus 10, and then cross out this guy. So x squared is 2.86 10 to the minus 10 times 0.22. And then you take a square root of that, you can get your answer of 7.9 times 10 to the minus 6 molarity. So they said is do the shortcut, you don't have to check, so I'm not going to worry about checking. But if you have to check, remember how do we do it? Take the x divided by 0.22 times 100. And you can check to make sure it's less than 5%. Okay, so now that we know x is hydroxide, we can get POH first. It's minus log of x 7.9 times 10 to the minus 6. So my pOH is 5.10. So my pH, remember, is going to be 14 minus that because pH plus pOH will add up to 14. So 14 minus 5.1, I get my pH of 8.90. So definitely make sure you do 8.9. And then you have to remember, once you decide your ion is basic, you should expect to see a pH that's higher than 7. Now we want to learn about acid strength, how to judge acid, which acid is stronger and which one is weaker, according to some trends. Okay, so we have two kinds of acid. The first kind is called binary acid. Binary acid. Okay, so it's H and then something HCl, HBr, all that stuff. So this is a monoatomic ion. Well, it's just the simple ion basically. Okay, so here's an example. And the first thing we want to look at for the binary acid trend is the easier the proton falls off from this H binary acid here, the stronger the acid will be. Acid strength is defined by how many H plus it can produce or how many ions it can split into. That's why we have the K term. So the more K, the bigger the K, that means it favors the product side, which is the ion side, the more H plus is falling off. So the first thing is we want to know is the easier the H falls off, the stronger the acid will be. Okay, so let's take an example. We have HF. There's a group 7 halogen ion, so HCl, HBr, and HI. Okay? All right, we're going to go down a group. Now, when you go down a group, what happens to the size? So if you go from the top of the periodic table to the bottom, every layer you go, you add an extra layer of shells, like 1s, and then this time was 2s, 3s, whatever. So it just gets bigger and bigger. So the size of this acid gets bigger, okay? Now when something is bigger, the bond lengths are longer, okay? So bond lengths will then get longer because the size is bigger. Now, a longer bond, when you learn in Chem 1, they say it's a weaker bond because it's easier to break. Single bond is the longest, double bond is the middle, triple bond is the shortest, okay? So this length is going to get longer as you go down. That means the bond gets weaker, okay? Now, if it's weaker, H plus will fall off easier. Okay, so the moral of this trend here, basically binary acids get stronger as stronger, there we go, going down a group. So that's if you have a list of acids and then we're going down a periodic table. Okay, sometimes you don't have that scenario. So another scenario, if it's go to the right or to the left of the periodic table. In that case, the size difference is not significant enough to make a difference. From H2S to HCl, yes, it does get smaller a little bit this way, but the size is so similar versus this one is a really big difference. The size doesn't matter as much. So along the same period, we actually look at electronegativity, okay? So the size is not big enough to compare. we compare electronegativity. Now, as we go from the left to the right of the periodic table, electronegativity increases. To the right. So when it's more electronegative for this Cl versus the S, the difference of polarity between these two are going to get bigger and bigger as you go across the periodic table. So basically, percent ionic character increases. So it's like more ionic, more polar, basically, okay? If that happens, H plus will fall off easier. More polar ionic character. Okay, so for binary acids, we have going down a group, it gets stronger, and going from left to the right, you look at electronegativity. The most electronegative one will be stronger, okay? So we have two examples between these two guys, right? Which one is stronger? So Cl is more electronegative than S. So Cl is going to be stronger. In this case here, HCl is stronger than H2S because of the going to the right of the periodic table. It gets more electronegative. And in this one here, HI is the strongest, HBr is the second, HCl, and then HF. I guess we write it down here. HI, HBr, HCl, and HF. Okay? So that's one example. So let's try to see if we can apply this, okay? Going down a group and going to the right makes it stronger because this side is more electronegative. All right, so rank binary acid. From weakest to strongest. In this case here, I was doing the strong to weak. Now they want to do the weak to strong. Okay, so the first example, A, they gave you H3N, HF, H2O. Okay, how would you rank this one? So this is, if you look at your periodic table, real quick, in case you forgot where your periodic table positions are. See, this is NOF here, so like S and Cl is here, so it's getting more and more electronegative as it goes to F, okay? So basically for A, you have F is the most onto the right, so it's the strongest. So weakest to strongest, and then you have H2O, and then you have H3N. Okay, now let's do another one. H2SE, H2S, H2O. Now, this one here on the periodic table is actually going down. It's on group 6. So I'm going to show you that periodic table real quick. In this case is OSSE, and then TE if we had it. Okay, so it's going down. Remember, going down a group, the one on the bottom is the strongest. So in this case here, the weakest is on the top, H2O, and then H2S, and then H2SE. Okay? All right, let's look at the third example, HCl, HBr, H2S. Now this one here, they mixed it up a little bit. So I'm going to draw you the position of where the Cl and Br and S are, in case you forgot. So this is group 7 here, okay? Group 7 will have Cl on the top, and then Br, and then sulfur is going to be on group 6. All right, so in that case here, the one on the bottom is the strongest still, okay, because it's the biggest So you always judge going to the bottom first. So Br is stronger than Cl, and then between S and Cl, who's stronger? Cl is stronger because it's going to the right. So it's going to go from H2S, the weakest one, going to the HCl and then HBr. HBr is the strongest because it's a lot bigger than these two are. Okay? All right. That's the first kind of acid. The second type of acid is oxyacid, has an oxygen in it. So I'm going to go ahead and change the page. Oxyacid looks like this. There's an H, and then earlier it was just the ion, right? Now it has an O and then whatever the other ion is, like some other group there, okay? So number one, to judge oxyacid is different than the way you judge binary acid. So that's why you have to keep them separate. Binary acid looks like H something. This one, oxyacid, has an O in there, okay? So the first thing to judge oxyacid is the more electronegative Y is, the more electronegative the stronger the acid will be. It's because the more electronegative, the easier it is to fall off because of the high ionic character. Okay, so on the periodic table, electronegativity trend goes up this to the top and goes up as you go to the right. So most electronegative on this top right corner. Okay, so basically, if we have an example, do HOI, and then we have HOVR, and then we have HOCl. How will we judge the strength here? Well, we have to look at the periodic table. Cl comes on the top, right here on the top, and then you have Br, and then you have I. Okay, so the most electronegative here will be the strongest. So you see how it's a little different from the binary acid trend, so you have to be really, really careful with that, okay? So oxyacid is based on electronegativity, and that's why you judge this way. Cl is the most electronegative, it will be the strongest. And then the weakest one is HOI. Now, if we were comparing the binary acid, the trend is different because we were looking at sizes there, okay? So let's go to the next one. The next one, after you judge electronegativity, if they both have the same electronegativity, you judge how many oxygen they have. The more oxygen, the stronger, okay? The more oxygen bound to Y, the stronger the acid. So in this case, if you have HClO4 versus HClO3, HClO2, and HClO. Okay, this one is the strongest because it has 4 oxygens. Everybody has the same Cl, so it's the same electronegativity. So the Ka, I'll show you the list here so you can actually see, but without the Ka, you could have judged the trend. This is the strongest, HClO is the weakest. Okay, so this one is a strong dissociation. Ka for the last one is 1, and then this is 1.1 times 10 to the minus 2. This is 2.8 times 10 to the minus 2.9. 2.9 10 to the minus 8. So you can see it is getting stronger with the more oxygen you have, okay? So let's try ranking some acids here. You want to rank from weakest to strongest, and your choices are H3PO4, HNO3, H3PO3, H3AFO3. So the first thing we want to look at is electronegativity, and then we can also judge the number of oxygens. Everybody has 3 oxygens here except for PO4 and PO3. Between PO4 and PO3, PO4 is going to be stronger because it has an extra one. Okay, but the first trend we look for is electronegativity. So going down a group, it looks like this. I'll draw it out. Nitrogen is on the top. And then you have phosphorus. And then you have... Okay? So in this case here, N is the most electronegative, so it will be the strongest. So HNO3 is the strongest. And then P is the next strongest in the list. But amongst PO3 and PO4, you have 2 options, right? So you got to put H3, PO4, and then H3, PO3. Okay? And then the weakest one is going to be the arsenic one. So H3, AS, O3.